In this video, we're going to do a bit of a deep dive into the idea of a categorical product. So we've discussed categorical products in previous videos, but we haven't really done a rigorous breakdown of exactly what it means to be a product in category theory and sort of how it relates to some of the other concepts that we've already seen. So we're going to start with just the generalized definition that we've seen in other videos and in other examples. So we know that a categorical product is a triple where the first object is an object in the category. So suppose we have some category C here, and we have objects A and B in C. Well, then the product of A and B, which is actually a triple, so keep in mind it kind of seems like A cross B would be the product, but remember that a full product in category theory needs to be all three of these objects in this triple. So the first one is an object, which we'll call A cross B. The second one and the third one are both what we call projection morphisms, and they both go from that A cross B object into both of the objects of interest A and B respectively. So you can see here that we have our objects A and B. We have our object in the category C, A cross B, and then we have our two projection morphisms, rho A and rho B. And so if you have a triple of this kind, where rho A goes from A cross B into A, and rho B goes from A cross B into B, then we have a product if for any object C in the category C, with morphisms F1 and F2 going from C into A and B respectively, then there must exist a unique morphism which we'll call theta going from C into that A cross B object, such that these triangles here commute. That is, F1 equals rho A after theta, and F2 equals rho B after theta. So that's sort of a direct, naive definition of a product in category theory. And it's not naive in the sense that it's incomplete or wrong, but it's just sort of lacking the broader context, which is that, as we said in a previous video, a product is actually an example of a limit in category theory. So if you don't remember what a limit is, or if you want to do a big deep dive review on limits, you can go see the video on that. But what's important to remember for this video in terms of products is that a limit is a terminal object in the cone category. And in particular, we said that a product was a limit over a diagram that consisted of just objects and no morphisms. So technically speaking, that's not quite correct, because in any diagram you can always implicitly refer to identity morphisms. So say we have our diagram here that has just A and B in it, the objects A and B. Say this is our diagram D. Well, we know that we can implicitly refer to identity morphisms, so there will always be identity morphisms, but we said that for it to be a product, it needs to be a terminal cone over a diagram with no morphisms other than those implicit identity morphisms. So it's just sort of a discrete category where you just have a collection of objects and obviously the associated identity morphisms on those objects. So the question that might jump to mind right away is, how does this definition line up with the definition of a product as a limit over a discrete diagram like this? Well, the first easiest way to maybe notice it is to say, well, if we take this diagram here that we have, so that's AB, so that would be sort of just this chunk here without any of the morphisms. Do you see how we actually have two cones over this diagram with A and B in it? If you don't see the two cones, maybe pause the video and try to remember what the definition of a cone is. Figure out what the two cones are and make sure that they do actually satisfy the definition of a cone. And they do. The two cones are obviously this expression here, this triple, is itself a cone, right? We have our vertex, A cross B, and we have legs for each one of the objects in our diagram. So that satisfies. But the other condition we need is that these morphisms need to commute with all of the morphisms in the diagram. But we don't have any morphisms other than identity in the diagram, so there's really nothing to commute with. So the definition is sort of trivially satisfied. So we have this expression here. This is a cone over A and B. And we also have this cone over A and B. We have a vertex C, and we have legs going from C into each one of the objects. And as before, there's no commutativity property to satisfy in terms of morphisms within the diagram. So we can actually say that this triple here and the triple consisting of C, F1, and F2 are both cones over this diagram D, consisting of just the objects A and B. But now, remember that C was arbitrary. So what this is actually saying is that if you can find me any cone with a vertex C or any other vertex, right, any arbitrary object in the category, if you can find me a cone with that vertex and legs going to each one of the objects in my diagram, then, according to this, there must be a unique morphism theta that commutes with both of those legs. So what is theta then? Well, it's a morphism going from the vertex of our arbitrary cone into our A cross B object here, which we said was the vertex of our product cone, and it commutes with all of the legs of the two cones, which is exactly what the definition of a cone morphism was, or a morphism in the cone category. A morphism in the cone category is a morphism going from the vertex of one cone into the vertex of another cone, such that all of the legs created by the two cones commute with that morphism. So with that in mind, let's rephrase this definition in the context of cones. So we can say that for any cone C, F1, F2 over D, there exists a unique cone morphism theta, which goes from C into A cross B. But this is the exact definition of a terminal object, right? For any object, which in this case are cones, there is exactly one cone morphism going into that cone, right? Because cone morphisms land in the vertex of the target cone. So we can see here that this definition is actually just a more verbose and naive way of stating that this triple here is a terminal object over in the cone category over our diagram D, which means that it is a limit. And because the diagram consists of only discrete objects A and B, it's a limit over a diagram consisting of only objects, which makes it a product. So we see through this discussion that actually there's a much simpler way to define products once we have the machinery of limits in place in category theory. So obviously it's a lot easier to remember a terminal object in the cone category over a diagram with only discrete objects than to remember this whole thing about, oh, if there's morphisms going from any object into our two objects, then there must be a unique morphism, blah, 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 right? It's a lot more succinct to remember. And again, as always, it's usually the easiest to remember when we remember it in sort of graphical diagrammatic form like this. So to sum that all up, a product, in fact, is a limit over a diagram containing only objects, with, of course, the technicality that those objects need to have identity morphisms, but it's basically a diagram that looks like this, just a collection of objects and their identity morphisms. Another benefit of this way of defining products is that this generalizes really nicely to diagrams of larger size. So say I added some object C in here, then this definition, a limit over a diagram containing only objects, well, this is still a diagram containing only objects. Obviously now we'd have to have 3 projection morphisms, right? And we'd also have to have 3 arbitrary morphisms coming from our arbitrary cone, because now there's 3 objects in the diagram. But essentially this definition applies to n or even larger sizes of diagrams. So suppose instead that D was a collection of objects, AI, for I in some index category, and this is our diagram D instead now. So we have maybe infinite or maybe a large number of objects in our diagram. Well, that's no problem. We just need a cone over this diagram, which is going to be what? Well, it's going to be an object, which we're going to call the product of all the AIs, the product over all the I's. And it's also going to need one leg for every AI, right? Just like any limit, so, or any cone. So this will need to have a bunch of projections, and maybe we call them PI, one going to each leg, AI, or one leg going to each object, I should say, AI. And then this is our product for even infinite or very large numbers of objects. But the key thing here to remember is that those objects are all that is in this diagram. There's nothing else. There's no morphisms between any of these AIs other than, of course, the technicality that all of the AIs have an identity. Now, when it's the case that for any family of objects here in our diagram, we can find a product in the category, then we say that the category has products, or the category has all products. So it may not be the case in an arbitrary category that a certain family of objects has a product within the category, right? Because obviously it's not easy to satisfy this definition necessarily. So there's a good chance that it might not have a product within the category. But in categories where any arbitrary family has a product, then we call it a category that has products. And in certain categories, it's the case that only finite families of objects have a product within the category. So if only finite diagrams like this, where this I is some natural number n, then we would say that the category has finite products or has all finite products. Let's now look at a couple of examples of products in categories, different categories. And we'll start with probably the simplest one is the product of sets. So what do we usually think of when we think of the product of sets? Well, we think of the Cartesian product, right? Sort of ordered pairs or ordered tuples of values from each one of the sets. So we'll see how actually this definition lines up exactly with what we would expect, is that the product of sets in the category of sets is the Cartesian product of the sets, which of course also exists in the category of sets. So let's take the example where everything is a set and every morphism is a set function. So we'd have our product A cross B. And what is A cross B? Well, A cross B is the set of all ordered pairs AB, where A is in A and B is in B. Pretty straightforward, right? This is the usual Cartesian product of sets that we're used to, of two sets in particular. And let's define our projection morphisms or projection functions in a very obvious way, which is that we just project the value into the set of interest. So row of A is going to go to A, and row of B is going to go from A cross B into B. And it's going to be defined, obviously, by row of A of AB is just whatever's in the front, and row B of AB is just going to be whatever's in the second position. The first thing to note is that this triple forms a cone over the diagram D, which is just the set A and the set B, right? Just like we're used to. So this is a cone for exactly the reasons we were discussing before. We have one leg going into each object, and we don't need anything to commute. So this forms a cone, and the question is, does this cone satisfy the definition of a terminal object in the cone category? Well, let's check. What do we need to do to check? We need to take some other cone, C F1 going from C into A, and F2 going from C into B. And we need to determine if we can find a theta for this cone. For any arbitrary cone, can we find a unique theta that commutes with both of these triangles? That is, we need to find a unique theta going from C into A cross B, such that, first of all, this diagram commutes, this triangle commutes. That's F1 equals row A after theta. And we need to have that this triangle commutes. That's F2 equals row B after theta. That is, for all x in C, for any object x in the set C, we must have that F1 of x is equal to row A of theta of x, and F2 of x is equal to row of B of theta of x. So if we combine these, well, this one is saying that whatever theta maps x to, the projection of that object into A has to agree with F1 on x. So what that's really saying is that the first blank to fill in here, right? Because theta of x goes from C into A cross B, so it's going to give us an ordered pair AB. And what this is saying is that the first object in this pair needs to be F1 of x, right? Whatever the projection into A maps the result of this to needs to agree with F1 on x. So that means we need this to be F1 on x, because this is exactly what gets projected into A, right? And then the same is true on this side, but of the second, F2 of x. And notice that, so this satisfies these definitions that we need. And also notice that we don't have any choice whatsoever in what we assign to theta of x for any x, right? So what this is telling us is that this theta x is actually a unique mapping. I just need to agree with F1 on every x in the first slot, and I need to agree with F2 on every x in the second slot. So I have no choice. I only have one way of defining theta x. And so it turns out that that's what we have. We have that this triple is a product of A and B in the categorical sense, not only in the Cartesian sense. Now it's important to remember here and make the distinction between the Cartesian product and the categorical product. The Cartesian product is just this set, right? A cross B, the set of all ordered pairs. But even though you may hear people loosely refer to this as the categorical product of A and B, really the categorical product of A and B is the triple with that as the object and then both of the projection morphisms. So remember that a product in category theory is a triple, not just a set. That's really important to make that distinction. Another distinction to make between the categorical product and the Cartesian product is that there's actually only one way to construct the Cartesian product for any two sets, right? It's just all the ordered pairs of objects in those two sets. This is the set right here. But remember that in the categorical sense, a product is a limit, and limits are only defined up to isomorphism. And so what that means is any object that's isomorphic to A cross B can also satisfy this definition and will satisfy this definition, because if it's isomorphic, then it will also be a product, right? It will also be a limit, so it will also be a product. And what is isomorphic to A cross B in the category of sets? Well, what's an isomorphism in the category of sets? It's a bijection, right? So literally any set that has the same cardinality as A cross B is going to be a product of A and B in that set. Whereas some arbitrary set that just happens to have the same cardinality as A cross B is not going to be considered the Cartesian product in the Cartesian sense, right? So that's another important distinction to make. Another interesting result we can get is that notice that A cross B, if we think of A and B as groups this time, so let's say we can have almost the identical discussion with groups, because we know that A cross B, when A and B are groups, is a group itself, right? The Cartesian product, or usually we refer to it as the direct product of groups is a group. And not only that, but the projections from that group back into our original groups, A and B, are both homomorphisms. So what does that mean? Well, that means that all of these objects that are in this triple exist in the category of groups when A and B are groups. So effectively, this whole discussion that we've had about this cone will apply just as much to groups as to sets, as long as we're sure that all of these are groups to begin with, or groups or group homomorphisms. But the only key thing to prove here is that for any given C, this function that we've defined, C into A cross B defined by this, is a group homomorphism. And that's a very easy proof. If you want to try that as an exercise, should be about a one-liner to prove that this morphism here is in fact a group homomorphism for any given C. And if that's the case, then all of this discussion applies to the category of groups, and we have that the direct product of groups corresponds to the categorical product of groups in the category of groups. For the next example, recall that we can represent a partially ordered set P less than or equal to by a category, and we do that by taking the set P and the order relation less than or equal to, and setting up a category Poset P less than or equal to, where the objects are just the objects in the set P, and the morphisms simply try to capture this order relation. So if M is less than or equal to N in P, then we have one unique morphism going from M to N. And if M is not less than or equal to N, then there is no morphism going from M to N. So fairly straightforward. It's just trying to capture this order relation by the morphisms in the category. So the question is, what does a product look like in this category? Well, to know what a product is, we need to know what a cone is in this category, right? Because it's a terminal cone. So what would a cone look like in this category? Well, if we have a cone here, C over the diagram consisting of just A and B, where objects A and B are objects in this partially ordered set, then we must have that C is less than or equal to A, right? Because we have a morphism going from one to the other. And that's what that means. If we have a morphism, there's only one, and it means that it's less than or equal to. And also implies that C is less than or equal to B. So that's what a cone means. If we can find a cone, it means that the vertex of the cone must be less than or equal to both of the objects in our diagram. And so in this case, if we found a product which was a terminal cone, then it would mean that A cross B would have to be less than or equal to A in the same way, and A cross B would have to be less than or equal to B. But not only that, because we found the cone that we need for our product, but in order for it to be a terminal cone, we need to have that anytime there's another cone over A and B, that there's a unique morphism going from C into our product A cross B. And so effectively what that means is that if we have some cone like this, where C is less than or equal to A and C is less than or equal to B, then it must be the case that C is less than or equal to A cross B, right? Because we have a unique morphism. And so because we have that unique morphism, that satisfies this definition, implying that we must have C less than or equal to A cross B. So if we combine all of that, we have that the object A cross B has to be less than or equal to both A and to B. And anytime we have another object C that is less than or equal to both A and to B, then it must be the case that C is less than or equal to A cross B. And so if you think about it for a second, which object would satisfy that property? Which object, which again has to be within this set, right? Because the object within the product is just another object in the category. So which object in the category P or in the set P would satisfy all of these conditions? Well, it's the greatest lower bound, right? The greatest lower bound is obviously less than or equal to both A and to B. The greatest lower bound of A and B, that is, of course. The greatest lower bound of A and B is less than or equal to both A and B, of course. And if there's some other object that's less than or equal to both A and to B, then it has to be less than that. So that means that it's a lower bound for A and B, and it's greater than all the other lower bounds, or greater than or equal to all the other lower bounds. So the product of two objects in the category Poset P less than or equal to is the greatest lower bound of A and B, the two objects in our diagram. So this is a good example to show that sometimes our idea of a product intuitively, for example in the category of sets and groups, lines up with the idea of the categorical product. But sometimes the categorical product is kind of surprising, like in this case, right? We wouldn't expect necessarily just by looking at it that the product of two elements in a partially ordered set based on the categorical definition would be the greatest lower bound. And another important thing that it shows is that these projection morphisms are important to specify explicitly because we don't actually know exactly what they are. They could be sort of that natural projection like we were showing from the Cartesian product to one of its halves, or it could be one of these partially ordered set morphisms that sort of follow this kind of strange definition. So this is just a good example to show that products are not always what we expect them to be in other categories. So to sum up everything we've said so far, we came into this video with sort of a more naive definition of what a categorical product was. We said it was an object and two projection morphisms coming out of that object, which go into the two objects in our discrete diagram, such that anytime we had another object with two morphisms going into each object respectively as well, there must be a unique morphism going from that object to our sort of product object, and such that these two triangles commute. And we actually found out that that definition coincided with what a limit was over a diagram with two elements in it, or two objects in it. And we said that because it lined up with the definition of a limit, we could actually define products in this way, which is that a product is a terminal cone over a diagram with only objects in it. And of course, we also generalized that to larger diagrams. So if D is any diagram consisting of just a collection of objects as well as their identity morphisms, then the product is going to just be an object in the category, which we'll call the product over all the i's of AI. And we have, just like in any cone, the collection of legs going to each of the objects. So that is, we have a projection morphism for all of the I as well. We then went on to look at a couple examples. We saw that the category of sets has products and that it lines up with our usual notion of Cartesian sets. We found that group has products and that it lines up with our usual notion of direct products on groups. And an interesting thing to note aside here is that the category of rings does have products. And as usual, it's a very similar proof. It's the direct product of the rings. But the category of fields does not. So if you're interested in why that is, you can look into it. There's a few different proofs. Some are a little simpler and some rely on sort of more categorical arguments like this. And finally, we saw that a partially ordered set has products, and it might not be what we expect, but we found out that that was actually the greatest lower bound of the two objects that are in our diagram, or of the many objects that are in our diagram, right? It could be the greatest lower bound of a whole bunch of objects. So that concludes our discussion on products.